What's next, Emily? A telescope on a balloon? And welcome back to another edition of the Syzygy podcast. My name is Chris, sitting opposite me, as ever, at the microphone, Emily Brunston. Hi, Emily.
Hello, hello.
So, back in episode 36, we talked about a telescope on an aeroplane, which at the time seemed ridiculous. If you think about it for more than about 30 seconds, you think, no, it can't possibly work having a telescope on a plane. Turns out you can do it. And Emily's seen it. She's been on the plane and she's, taken photographs of herself with the telescope on the plane. It's a real thing and that works. And at the time, I made a joke, which was, well, if you can have a telescope on a plane, what's next, Emily? What is it going to be? A telescope on a balloon? Wow. Turns out...
We actually do have telescopes and balloons.
Turns out that's a thing. So, well done, Chris. That was supposed to be, an amusing aside.
Well done for putting down decades of research in balloon astronomy.
Yeah, sorry, everyone. I mean, I guess if I'd thought about that a little bit longer, I might have come to the conclusion that that's actually possible. So we're going to talk a little bit about telescopes and balloons today, but we're talking about that as a sort of a preliminary lead-in to talking about something which I think is one of the most amazing things in the modern history of cosmology and astrophysics, which is a little thing called the cosmic microwave background, the leftover glow from the Big Bang itself. So we're going to be talking about that today. But first of all, balloons, telescopes, what?
What?
How does that even work?
Well, actually, the two things that you just mentioned go together, right? Mm-hmm. So what we're looking for is we're looking for microwaves. So this is part of microwave astronomy. And microwaves come from the universe. They come from lots of things, but mostly what we're doing when we're talking about microwaves is looking at the CMB. So it's cosmic microwave background. And one of the ways that we used to do this very, very successfully, and actually still do some of the more modern flights, is with balloons.
Now, these aren't sort of Winnie the Pooh style, tying a bunch of balloons to a telescope and watching it float away. I'm guessing these are sort of your very, very large, what are they, sort of weather balloon type things?
The basic principle is actually the same. You tie your telescope to a balloon and watch it float away.
It's still a balloon,
but it's a bigger balloon.
It's not sort of, Pixar's Up.
No.
Style, we're going to float away with 800,000 balloons attached to our very large telescope. It's not that. That's my mental image, just so you know.
That would be fantastic.
That would be great, but it's not that, is it?
But they are quite pretty. They're big silver weather balloons.
Yeah, and really big sort of long teardrop or inverted teardrop shapes, aren't they?
Yes, and they change shape as you go up through the atmosphere because, of course, all the pressure changes. So they grow as the pressure goes down as you go up higher and higher.
Right, and they go very high.
Very, very high. Yes, the one we're going to be talking about today actually went up 42 kilometres into the atmosphere.
That's a long way. That's basically to space, except it's not to space because a balloon wouldn't work in space, would it?
Yeah, and that's the whole point. We want to go basically to space because in microwaves, it turns out the atmosphere is super absorbent to that type of light. So we just don't get very much on the ground. If you want to get more, you've got to go above it. Same principle as Sophia, actually. You're going to go above the most of the atmosphere or as much as you can. So stick things up high.
So that makes sense. It's the same with Sophia. My main concern about this, Emily, because I am concerned, I worry about these things, is like telescopes need to be stable, don't they? Really? Like if you're looking at something with a telescope, doesn't matter kind of what telescope it is, doesn't that need to be a fairly stable observation? In which case, strapping something to a balloon doesn't feel to me like the most stable of environments. Am I wrong?
You're not entirely wrong.
Okay, good.
So we don't necessarily...
I like being not entirely wrong.
We don't necessarily do this with the kind of telescopes that we use for optical light to get those wonderful Hubble pictures, for example. But we do it with different types of telescope, with different types of sensors on them as well. So we have to sort of cast away the idea that we're looking through a camera lens at the universe at this point. In fact, we're using some very sophisticated detectors called bolometers. Are
they bolometers because they're on a balloon?
No, it's just a fun coincidence.
I like that, a bolometer on a balloon.
Yeah, no, don't say that 10
There's
times
a kid's
fast.
book in that.
So bolometers basically take incoming light and they're temperature sensors. So they can take the incoming light, basically how much the temperature rises in the bolometer tells you the intensity of the light that hit it. to how bright it was. And you basically do a color by numbers way of looking at the sky by pointing your different barometers at different directions. When you say, oh, that's a 7 over there, and then it's next to a 3, and then it's next to a 2, and then it's next to an 8. So you can basically build up a picture just by using these very nice detectors.
So you're not talking about like zeroing in on an incredibly small bit of sky in the way that, say, Hubble does, in order to get these extraordinarily high resolution images of objects. You're pointing in a specific direction in the sky in order to get a general, in this direction, we're measuring this amount of stuff.
Yeah,
That's
exactly.
the kind of idea. There's this many microwaves coming from that bit of the sky.
Exactly. We don't do all sky mapping using these balloons, right? But yeah, there's been quite a few of them, very, very successful. In fact, I loved all the acronyms, so I wrote them all down.
Acronyms in astronomy are always good. So
always good.
Hit me with it.
All right.
Give me a good one.
I found at least 14 different balloon missions.
Wow. Okay.
Most of them happened in the 1990s up until 2000.
The 1990s were a boom era for balloons in astronomy.
But here, are you ready for this?
Yeah, I'm ready.
Right.
Go.
Okay,
Hit
so
me.
the list includes Argo, FIRS, MSAN, Maxima, QMAP, BAM, Boomerang, Archaeops, Arcade, Top Hack, EBEX, Spider, and the list goes on.
So hang on, a few of them leaping out at me. Spider's leaping out at me, which is a bit disconcerting. These are all acronyms?
These are all acronyms, and I didn't write down all the acronyms.
What was the one in the middle there? Was it
Boomerang?
Boomerang, not Billabong. That's the other one. Boomerang.
Yeah, of course the Australian picks up on the Boomerang one.
Well, yeah. So Boomerang as an acronym, what's that?
Well, actually, I thought that Boomerang is one of the most important ones.
Yeah.
It's really, really nice to pick out because it's one of the first measurements that we actually made whereby we were able to tell the shape of the entire universe.
Wow.
Yeah.
Okay. And what shape is it?
Well, it turns out the universe is flat.
Right. Okay. Completely flat or just mostly flat?
As flat as we can possibly measure it to be flat.
Wow. That is flat.
It's
That
quite
is
flat.
Because the alternatives are not flat, but in what way? Like how would the universe not be flat? What shape would it be if it wasn't flat?
This is incredibly difficult to imagine. So when we say flat, we don't necessarily mean it's like a flat Earth kind of flat universe kind of thing. We don't all live in 2 dimensions, obviously. But what we're talking about is the curvature of space-time, and space-time's kind of the founding fabric of the universe. So does it curve kind of outwards so that you get this kind of bubble? Does it curve kind of inwards so that you get something a bit like a saddle? Or is it just completely smooth and flat?
Yeah, and when we're talking about curving here, I mean, this is the really hard part. This is curving in 4 dimensions, which really, really hurts. I mean, it's hard enough to think about these things in 3 dimensions.
Yes.
You know, when we talk about the surface of a sphere, we're talking about a 2-dimensional thing in 3-dimensional space. And we're used to that. That's the sort of thing that we look at all the time. Trying to imagine a 3-dimensional, okay, and that 4-dimensional, that's even harder. So, but one thing that you can think about perhaps is, correct me if I'm wrong, I could be wrong about this, but to the best of my understanding, if the universe is curved kind of like, you know, a sphere, but 4-dimensional sphere, it's curved around that way as opposed to the saddle shape, then you could head off in a direction through space and keep going. And eventually you would wrap around that sphere and come back to where you started from, even though you were going off in a straight line.
Yes.
That's the idea.
Yes.
It might take you a really long time to do that, but that's the notion of a closed universe, as opposed to the other one, which is open, where you just keep on going forever.
Yeah, although there are different ways that you can keep, you can loop back around in a flat universe, but it gets really, really hard to imagine it.
Cosmologists don't at me, you know, it's been a while. I haven't studied this in a while, but that's there. You know, there's something in that.
The point is that it tells us something about the ultimate fate of the universe, and that's the important thing. So it tells us, is the universe going to keep, for example, depending on other forces, the dark energy that we're also not going to talk about.
Not today.
But depending on other things that are happening, you can say things about, is the universe going to end where everything's flying apart forever and ever and ever? Or is it going to end where eventually everything kind of slows down, stops, and then comes back back together in the opposite direction?
Yeah, a big crunch.
And a big crunch. So it's a really important measurement to tell us something about how the universe is going to evolve.
I mean, not important in a sort of, is the universe going to end next Tuesday kind of way. Important in a, what is this thing that we live in kind of way. You know, it's one of those kind of questions. It's not important for anyone's everyday life, but it's important.
It's very important.
Yeah. Anyway, so
Boomerang.
Boomerang was where we started that. Yeah. Boomerang stands for what, Emily?
Balloon observations of millimetric, extragalactic, radiation, and geophysics.
Boomerang. We're missing an R, aren't we? Isn't there an R missing? We got all the
radiation,
other letters.
radiation.
Oh, no, radiation is in there. Okay. All right. Yeah, fair enough.
Yeah.
I mean, they worked hard for that one. I think
they really
for that.
did. And you're going to love why they call it Boomerang.
Why?
Because it's a very, very clever balloon. Basically, you send it up in a particular place on the Earth and it comes back to you.
Wow. That's not bad for a balloon. What, is it tied down? How does that work?
No, we launched this balloon from McMurdo Station in Antarctica, and then it was carried by the polar vortex, basically up and around the South Pole, and then back down again to nearly the place where it left off.
That is clever. So it basically is a boomerang.
It
goes
is.
up, goes around, comes back down again.
Really nice, isn't it?
Nice.
Yeah.
So they worked hard for that acronym and they knew where they wanted to get to.
They knew where they were going.
So there's a lesson there for acronym builders everywhere, is have it built into the design spec from the beginning, I think. So, okay. So those are all of our balloon telescope missions.
Yes,
there's a whole bunch of them. This is not a dumb idea. It's not as funny as I originally thought. It's a thing.
And it gets you on the cover of Nature.
Well, not me personally, but it does.
The Boomerang team definitely did.
Really?
Yeah.
Okay.
For those measurements of the geometry of the universe.
Okay. So this is a big thing. It's an important thing, and I should just learn to mind my manners, basically, and not upset the astronomers working with the balloon. So sorry, everyone. But look, importantly, these are all things which are measuring this absolutely amazing thing about the universe called the cosmic microwave background. Or maybe they're not all doing that. Are they all doing?
Most of them are.
Most of them are. The CMB, cosmic microwave background. So we should probably talk about that a bit, because this
Definitely.
is really, really good stuff. So Emily, where do we start with the CMB? Where did it start?
Well, let's break it down into what it actually is. I mean, We've got cosmic.
Yep.
Microwaves.
Microwave.
So it's coming from microwaves. And it's background. Now, that's the key word here if you want to figure out where this is coming from. It's a background because it's absolutely everywhere. Every direction in the sky you point, you will see cosmic microwaves coming towards you.
And this was one of the really interesting things, that like the story about how this was discovered, I think is absolutely fabulous. What were the two astronomers' names?
Penzias and Wilson. Well, they weren't astronomers. That's
no, they weren't.
Thing.
That's right, were they? They had the big horn-shaped microwave instruments. But what were they doing?
So they're working at Bell Laboratories. This is in 1964, Penzias and Wilson. They're working to try and see if microwaves could be used as a more efficient method of kind of radar communication.
Right. Because, of course, microwaves are used in communication all the time now. You know, your mobile phone uses microwaves to communicate back and forth. So, you know, it's not just something that you find in ovens in your kitchen. This is it's around us all the time, and it's useful all the time. And so they're experimenting with this down at Bell Labs in the States, and they've got this huge kind of weird angular horn-shaped device, which is, you know, they can point it in different directions and use it to send and receive microwaves. And they find this signal. There's this background, sort of very low-level background hum at a particular frequency.
Yeah, a bit like a hissing.
Yeah, a bit of a hiss. And it's really annoying because it's getting in the way. Like, we've got to get rid of that so that we can make these clean measurements. And they can't find the source of it. And where the hell is this thing coming from? They even thought that it was as a result of pigeon poo, that birds had been roosting inside this huge metal horn shape, and the poo was reacting with the metal and causing electrical interference to give this background hum. Turns out it wasn't pigeon poo. It was, in fact, the universe. They were tuning in for the first time to, you know what, everywhere we point, every single part of the sky, there's this background noise. What the hell is that? But around the same time, people were kind of calculating that, you know what, maybe there should be a background hum in the universe. What was that from?
From the Big Bang.
From the Big Bang. How does that work?
So, well, if you think about we've talked about the Big Bang before, and how we have this sort of kind of well, something strange, quantum fluctuation, rah, rah, rah. We won't go into that.
Quantum, something, boom.
Yeah. Okay. And then you had the universe in existence. And the universe expanded very, very rapidly. And it was very, very hot and very, very dense in the very initial stages. And we talked about, for example, in an earlier episode about how you form elements out of that. If you come all the way back to this point in time when there was a huge period of the universe's history where we can't ever probe it because we don't know what happened when we don't have any photons that come to us from this time in the universe.
Right. I mean, our observations of the universe, ignoring gravitational waves for a second, because that's very, very new. So ignoring that, pretty much everything else we do involves photons of some kind, light. Whether that's visible light or ultraviolet, infrared, radio waves, gamma rays, whatever it is, it's all the same stuff. It's all photons. So without photons, vast majority of astronomy is done. We've got nothing. And so there aren't photons, we can't see it.
No, so in the very early days of the universe, it was just a hot, messy blob, right? And photons were interacting with the electrons and the very first particles, but they were interacting and going back and forth and so on so much that they just couldn't escape.
Right, it was this impenetrable soup of charged stuff. And it was like that because the universe was so hot that atoms couldn't form, right? Whole atoms. And the thing about an atom is that, I mean, hydrogen, for example, you've got a proton in the middle, which is positively charged, and an electron around the outside, which is negatively charged. And so if you look at that from a distance, it's neutral. There's no charge. The charges cancel out, which means that photons can just whistle on past without seeing anything unless they get really, really close into the atom. So when you've got protons and electrons way too hot to form atoms, then the whole thing is just this big soup of charge, electrical charge, and the photons are going, there's a charge over there, charge over there, and they're just bouncing around in this crazy charged soup, and you don't get any photons coming off to tell you what's there.
Yeah, and the universe kind of continues expanding and continues expanding. But as it's expanding, it's cooling down.
Yep.
So as you start to cool down, the temperature starts to drop, and eventually you get to this point where the hydrogen atom actually comes together. It's
reaching this point where it's cool enough for those charges, the positive proton and the negative electron, to be able to go into this lower energy state of an atom bound together. If it was hotter than that, then the electron would go, no, I'm off over here. But it's cool enough that, no, this is a nice place to be. And atoms can form.
And you have hydrogen.
They do form, and you've got hydrogen. But that means for the photons that suddenly the universe, and it was quite quick, wasn't it? Quite suddenly.
It happens very quickly because you've got this ultra-dense material. So once it starts to happen in one area, it's kind of like a chain reaction that propagates through. Because once you start to lose photons out of sort of one side of the universe, if that makes any sense, then you basically rapidly cool the rest of the plasma blob. So what happens is if you can imagine a little bit like the fog lifting in the universe. You had this blob that you couldn't see into because it was opaque. And then once the atoms formed, the hydrogen atoms formed, the photons were able to be free and escape from that blob and therefore travel out through the universe and that universe actually became transparent.
Which is really interesting because if you think about that for a second, just before that moment, all of these photons are bumping around the charges because the charges haven't made atoms yet. So they're all bumping around. And if there's a bit of the universe which is a little bit more dense or a little bit less dense, then you're going to have much more charges in the dense bit and much fewer charges or a bit fewer charges in the less dense bit. And so the photons are going to be interacting with those charges a little bit more in the dense bit and a little bit less in the less dense bit. And then suddenly the universe changes from charged, soup, opaque, photons can't travel through it easily, to suddenly it's transparent and the photons can just clear out. And they're carrying with them at that point the signature of what the universe looked like in terms of its density, where the stuff was at that point in time.
Yeah.
That's what the cosmic microwave background is at that epoch where everything joined together into atoms, then you've got this picture of the universe wafting out, waiting for us to look at it.
And that's the beautiful thing. These photons are the oldest photons that we can ever possibly look at, because they were emitted from this recombination period, something like 380,000 years into the history of the universe.
Now, 380,000 years is a long time in human timescales, but we're talking 380,000 years out of 3.8 billion
13.
years? Sorry, 13.8 billion years of the universe, which is a tiny fraction of the life of the universe. So these are really old.
Really, really old.
And these guys with their big horn-shaped microwave antenna thinking it was bird poo, turns out it's not bird poo, it's the oldest photons that we've seen, which is kind of a cool discovery.
And a brilliant thing is you've probably seen some of them as well.
Really? How?
So I think the statistic is something like 0.5% of all the static that you get in old television receivers is actually noise created by these photons drifting around.
Right. So if anyone listening out there is old enough, as I am, to have seen a television which used to get analog pictures through the airwaves, through as radio waves coming across the world from the towers to my little aerial. And if you tune that TV off the station, then you just get static. It's your classic sort of static of noise, but on the picture on the screen is a lot of little random dots. Because you're just basically trying to tune into whatever's there in the air. There's no strong signal. But you're saying what percent?
Something about 0.5%.
0.5% of those dots, right? So one in every 200 of the dots on the screen is from a cosmic microwave background photon, which is kind of cool.
That's very
and
cool.
Kids today won't get that because no one sees static anymore because it's all over the interwebs. No. Isn't that sad? Yeah, kids, go and get yourselves an old school TV and then you'll figure out what
Just sit down and watch the CMB for a while.
Yeah. It's nice.
So that's really interesting. So we have our photons that were left the universe. Now, the universe was very, very hot at this point, right? It was something like 3,000 degrees still.
Yeah, it had cooled, but not that much.
Now, what's happened? Now, if you think about temperature and light, we have this relationship between when you are at a temperature, you emit light. So you and I are emitting light in this room. We're emitting it in the infrared. So that's how infrared cameras work.
Yeah. That's how those see in the dark cameras that you see in spy movies and war movies. That's how they work, because they're seeing the light that we emit because we're warm.
Yeah. And the hotter you are, the higher up the spectrum the light you emit. So the sun is very, very hot on the surface, right? It's about 6,000 degrees. So it's emitting light that we can see with our eyes.
Yeah, as well as lots of light that we can't see with our eyes. But the reason that our eyes see the way they do, presumably, is because evolution said, hey, there's a lot of light over here. We should have a look with that. See if that works. Anyway, the sun emits what we call
the most
visible
common
light.
light, if you like, the most common number of photons come from the visible spectrum from the sun. And so as you cool down, if you go down to about 3,000 degrees, this is actually the temperature of a very cool star. Right. So if you think about some of the reddest stars in the night sky, the coolest ones that we have on the surface anyway, then this is about what the temperature of the universe was at this time. Now, those would have emitted something like very, very red photons to maybe just a little ways into the infrared.
Okay.
So why are we looking at them in microwaves now?
Because microwave is not visible. You can't see microwave.
It's
light.
Further down the spectrum more.
You can't see the signal that's coming to and from your mobile phone. You can't see that going around. And so that means that microwaves are much lower energy, aren't they?
Yep.
Much longer wavelength, much lower frequency, right? They all mean the same thing. So if originally the universe was at 3,000 degrees, it's not anymore. We don't see the universe as this incredibly hot thing. Why not?
Well, it turns out the universe has gotten a whole lot bigger since then.
Right. So the whole expansion that allowed this thing to happen in the first place, the transition from completely opaque to completely transparent when all the atoms formed, that's still going on. We're still expanding.
Yep, and it's cooled all these photons down so that they used to be at a temperature of 3,000 degrees. Now they're at a temperature of, well, in Kelvin, it's about 2.7 Kelvin, which in our Celsius measurements is minus 271.
Something like that.
Yeah.
I mean, if you've never used, you out there in listener land, if you've never used Kelvin before, it's really, really easy. It's just like Celsius or centigrade, except that it starts at zero, absolute zero, where virtually nothing happens, is 0 Kelvin, which is minus 273 degrees Celsius. And that's 0 Kelvin. And so we're talking how much above that?
2.7.
2.7 degrees above nothing, which is, that's very cold.
Very cold. But it's
not nothing.
It's not nothing. So it's in the microwaves, this temperature. So if you were at 2.7 Kelvin, you'd give off microwaves.
Yeah. So around the same time that this thing was experimentally discovered, theorists looking at the universe in equation form going, well, hang on, the universe is expanding and there was a big bang. Maybe after that there would have been this period of the universe being opaque, and then it could have transitioned to the transparent bit. We should see that. We should be able to measure that. Let's do a quick calculation of what that would look like. And it came out to be staggeringly accurate, didn't it?
It's one of the most perfect agreements between theory and observation that we've ever had in science.
And one of the lovely things about it, if you look at the way the data fits the theory, right? The theory says that the universe should have been this thing, would have been a thing called what physicists call a black body. And a black body is one of those hard things to wrap your head around as an undergraduate physicist. What are we talking about, black body? But all it really means is that you can, like, all of the radiation, all of the light, all of the photons that are hitting this thing, all of it will get absorbed. It's completely black. Anything that hits it will get absorbed. That will raise its internal energy, and then it'll give off, as we said before, it'll give off some photons because it is a particular temperature. But the point of a black body being that it can absorb everything that hits it, as opposed to stuff that we see around us, which absorbs some and reflects some and transmits some.
Yeah. It's basically a perfect object in the universe. So it's just as a temperature, and it has a perfect spectrum because it's got this beautiful temperature and it's putting out the light of that temperature.
And that's what the universe was, partly because it's the universe. It contains all the radiation, so it's going to absorb all of it at some point anyway. But just before the atoms formed, just at this transition period, all of that light was being absorbed. It was all bouncing around. And then suddenly, bang, it changes. And we get a glimpse of the radiation at that point in time. And so the mathematics of that black body is really, really well known. We knew that really well. It's a fairly simple equation. You can write it down and predict what would that be, and you measure it, and it's the most stunning lineup of here's the data that we measure, here's what it should be, and they are spot on. It's extraordinary.
It's really, really lovely.
Yeah.
So Penzias and Wilson got the Nobel Prize for this in 1978, and ever since, the cosmic microwave background has completely revolutionized cosmology for us, because now we have a tool to look at the very, very early universe. We've never had such a probe before. I mean, we can see far back into time when we look at very, very distant galaxies, but we're still talking about a billion years or so after the Big Bang. To go from 1 billion years down to just a few 100,000 years was an incredible achievement.
Yeah, that's a huge difference. Now, you might sort of think, well, hang on. I mean, okay, you've got a measurement of the temperature of the universe now, and you can see that microwave background in all directions in space. It's everywhere. So what? I mean, that's basically one number, right? The universe is this temperature. But it's not that simple, is it? There's a subtlety to it.
There's a really, really important subtlety, and that is that it's not perfectly smooth. Now, when you see pictures of the cosmic microwave background, you'll see that there's red spots and blue spots, and there's all this beautiful structure. And you see a big oval shape because this is basically an all-sky image that's been put onto a piece of paper, basically.
Yeah. In the same way you can't make a map of the Earth perfectly flat and have it work really, really well. If you're going to map the sky, you kind of got to do it to a particular shape, and it's not going to be rectangular.
No.
It doesn't work
so
that
it's
way.
kind of, if you took the whole sky and then sort of ironed it out and smoothed it down onto a piece of paper. Yeah. So you see this lovely oval, and you see all the colours and the shapes and the structure and that. You always have to remember that structure is tiny. It is not obvious. It is something like 1 in 100,000 the difference in temperature that you're seeing here. So
we are still basically saying, what is the temperature of the universe when we look at in terms of its microwave radiation? You know, this is the temperature that we're measuring from the microwaves that we receive, and it's roughly 2.7 Kelvin, but tiny little wiggles above or below that average number. And what is that telling us? What's that saying?
Well, it contains huge volumes of information, because remember that this is not just the photons that came from this very, very early time in the universe. They're carrying the information of what the universe was like when they left. If you like, this surface of last scattering is kind of what cosmologists like to call
What a
it.
lovely term.
Yeah, this period when these photons were released from the universe into the universe, or part of the universe.
Through the...
Yeah. Anyway.
Released from the universe.
In the universe. And so they contain all the information that they had when they left. They also contain all the information that they've picked up on their journey towards us.
Because it has been a long time.
It's been a while.
They've been traveling for basically 13.8 billion years. So... That's a long journey.
So there's lots of different types of variations in the cosmic microwave background that we study to find out early conditions in the universe, and also how the universe evolved over the intervening 13 billion years.
So you're able to tease those two things out.
Yeah. And we're able to get a lot of information. So I was summarizing, and I got into a lot of rabbit holes when I was reading.
There's a lot of weeds on this one. Yeah.
I mean, we can't understate the importance of the cosmic microwave background and how much information it contains. Some of it incredibly technical. But I tried to sort of summarize all the things that we knew from the CMB into some kind of overarching themes to give you a flavor of just some of the things that we've learned since discovering this. So the first sort of theme, if you like, is we've learned a lot about our origins. The cosmic microwave background supports the model of the Big Bang, first of all. Not just because it exists, and it kind of should, but actually because it exists and it's super, super smooth. Now, if we came from another model of how the universe came to be, even a steady state model, you wouldn't necessarily expect there to be this smooth, uniform radiation from everywhere in the universe. And even if you can conjure up a way to make it happen in a steady state universe, for example, then you can't explain why it should be so perfect to within 1 in 100,000 parts.
So even ignoring the crinkly part of it, the tiny little wiggles in the cosmic microwave background, just ignoring that and looking at how uniform it is, that really supports. There's something really interesting about that. That really supports such an explosive beginning. You'd kind of think it might be the other way around. But...
It supports, it definitely. And it's not just the explosive beginning, but it's also this period that we have in the early universe called inflation, where the universe didn't just grow. It
really grew. It wasn't mucking around.
It took off.
And that's a topic for, add that one to the board, because inflation is a really big one. But the universe was already expanding because it's the Big Bang. That's what it's going to do. But then it went through a really quite extraordinarily interesting and difficult to understand period called inflation, where it just went from tiny to stupidly enormous in ludicrously small periods of time.
Yeah.
And
think about it as the most amazing growth spurt.
Yeah. I mean, just absolutely staggering. But what that would have done is any wobbles in density and differences in density and the way the universe would have been structured before inflation would have been smoothed out down to tiny little changes.
Yeah. So
through
if you
the course of this huge expansion.
Just like if you took a golf ball and you expanded it to be the size of the Earth, you wouldn't notice that there were dimples anymore.
No, you wouldn't really see those unless you were, a very long way away. But yeah, that's the kind of idea. So actually it supports, the cosmic microwave background's incredible uniformity supports these ideas, which is great. And that's before you even get into the wiggles in it.
Yeah. And then, and you can learn things about the age of the universe. So our most accurate age of the universe comes from the cosmic microwave background.
Because you can get that temperature so well, and you know where that temperature would have come from in the first place.
Exactly. And so you get your 13.8 billion years. I need to start saying 0.8. I've been on 0.7 for a while.
And it's been updated.
I think I need to revise my statistic there. Yeah, so 13.8 billion years. So that's kind of about the past, and obviously it tells us lots of other interesting things about that soupy glob mess. But you get an idea of basically some of the things that the cosmic microwave background can tell us about that. It also tells us about the present. So we mentioned already that it tells us something about the geometry of the universe. Are we a flat universe, or are we curved in some kind of way? It also shows a really interesting, and this is the photons having not gone through exactly the same life, if you like. If you look at a photon from the northern hemisphere and compare it to a cosmic microwave photon from the southern hemisphere, they've come through different parts of the universe to get to us.
Sure, yeah.
So they carry different information about the material that they've been through on their long voyage, if you like, to us. And what we can do with this is we can actually say something about the density of matter, because we know that matter interferes with space-time, and photons have to follow the curvature of space-time. On a practical sense, what it means is that mass and photons interact as the photons are traveling. So the photons that go through areas where there's a lot of mass, now we're not just talking passing a nearby planet or a nearby star. We're talking about those photons that might have gone through enormous galaxy clusters compared to those who just went through void space.
Right. And because we're talking about photons which have come to us over such a long period of time, we can talk about those scales. It's not, did it pass by a star? It's, did it go through some massive galactic cluster? What evidence do we see for that?
Yeah.
And so are you saying then that we can see in the signature of these photons the way the universe is structured?
Yes.
At large scale.
Yeah, because the photons that go through these massive clusters of matter, of galaxies and all the other bits and bobs that come with them, they end up being very, very slightly warmer than the ones that didn't. So you can actually see this kind of map of where the structure is in the universe based on the temperature.
And huge scale structure. I mean, we've talked before about, you know, the galaxy and then the number of galaxies that we've got around us in the universe. And it's, you know, there are galaxies everywhere. Go and have a look at that Hubble image there of the Hubble Deep Field, the Extreme Deep Field. There are galaxies everywhere. So what this is telling us is that at these really large scales, like this is not just sort of, you know, there's a galaxy over here and there's a galaxy over there. We're talking about huge clusters and superclusters and uber massive, stupid sized clusters of material in galaxies over here. But then there's also these sort of voids or superclusters along strings that are connected in these web-like structures throughout the largest scales of the universe, which is the sort of thing which boggles the mind that we can actually see that kind of structure in this way.
Yeah, and it tells us not only what the structure is, but kind of what it's made of as well. So the cosmic microwave background has given us the most precise numbers for actually the entire composition of the universe.
In what way? You mean in terms of sort of, you know, down to the element level, hydrogen and helium, that kind of thing? Or do you mean...
No, down to the kind of how much is ordinary matter, like ourselves,
right, yeah.
How much is dark matter, and how much is dark energy. And it turns out...
that's a fairly embarrassing statistic, really, isn't it?
Yeah, we're not much.
Yeah, like ordinary matter is what, something like 4% or something? 5%?
Yeah. So 95% is dark matter and dark energy.
So 95% of the universe is the stuff that we still don't get. So, you know, doing well there.
Yeah.
But it does mean that we're all still in a job, which is nice.
It is.
Yeah.
So that's some of the stuff that the cosmic microwave background sort of tells us about where we are now and what's going on. And it also contains information about the future. So,
sorry, what? The future? Go on.
The ultimate history of the universe, where we're going to end up.
I see.
So it tells us what cosmological models we should be looking at. And one of the things I really like about the universe in some ways is that when you talk about cosmological models, it seems like sometimes the most simplest ones seem to still be working, which you'd kind of think, well, we started writing down models for how the whole universe might be structured. Well, Einstein, for example, wrote down some, but at least 100 years ago, right? So, but those models seem to still work pretty well.
Yeah.
It's
like,
really...
those were the easy ones to work out, but surely the universe is much more complicated than that. Turns out, no, maybe not.
No, it seems to work just fine for most of the stuff that we observe. So we can use that to therefore predict, like we talked about before, the outcomes of what the universe will eventually do in infinite time. Will it keep coasting on and expansion will continue forever and ever? Or will expansion eventually stop, everything will turn around and collapse back down to a kind of inverted Big Bang?
Yeah. Just something you mentioned then, I'm always really staggered to think, I mean, Einstein's stuff was sort of, 100 years ago was when he was really hitting his stride, and the whole general relativity thing really changed the way we view the world. And that's 100 years ago, which sounds like a really long time. It was only 100 years ago. And when you think about the discovery of the cosmic microwave background, like that's only 50 years ago, we've only known about this stuff. We've only had this evidence of how the universe is for one professional astronomer's lifetime.
And even less than that.
That's amazing.
I mean, 1997 was supernova results for dark energy, right?
Yeah.
And 2003 was the last time we flew Boomerang. So we got some of these fantastic results about the shape of the universe that matched the supernova data. You know, this is new stuff.
This is new stuff. And it's really easy to sort of assume, we've known about this for ages. You know, even if you're learning about it for the first time. Well, surely this is stuff we've known about for it. No, it's not. This is new and it's exciting. You don't have to go back terribly far before the idea of the Big Bang didn't even exist. We didn't think that the universe had a beginning. It was always that way. Turns out, no. We've got all this evidence, including the cosmic microwave background, which is new, still new to humanity. I find that fascinating.
And the latest data release, which just came out, has just refined all these numbers to insane levels of precision.
When you say data release, from what?
So this is coming from Planck.
Right.
So Planck is our latest space telescope. So balloons played a really, really important role in the cosmic microwave background, but we can't omit the fact.
Can't beat a telescope in space, really, can you?
No, you really can't.
So Planck is the one. That's the microwave
So
one?
we've had a few, but Planck is the most recent. So Planck flew from 2009 to 2013. And the last data release from Planck just came out middle of last year in 2018.
So even though the mission finished in 2013, it's taken 6 years to get, or 5 years to get the last data release. Because there was a lot of data.
It's a lot of data.
Yeah. I mean,
it's the whole sky, right?
It's not a criticism.
No.
You know.
These things are huge. And whole sky survey. So these are how we get the big maps. And we're still looking at stuff in Planck's cosmic microwave background, but there seems to be one very, very elusive thing that we're looking for, and we just can't find, which is very, very interesting.
So what's that?
Okay, so we're going to have to backtrack a little bit here and just mention polarization.
Right.
So light can be polarized, and what that means is basically it can have a direction to the way that the electric and magnetic fields that make up light wiggle.
Yeah. I mean, light is weird, and we could talk so much about how weird light is, but light is weird in a couple of particular ways. One is that we sometimes talk about photons, and that's the particle of light. And light can be a photon, it can be a particle, but it can also be a wave, and that's quantum, baby. So when light is a wave, it wiggles in a particular direction. It has an electric field and a magnetic field, and they're at right angles to each other. But the electric field and the magnetic field wiggle up and down or sideways, and that's the direction of that field.
So my very base and completely incorrect, but kind of useful way of imagining this is if you have kind of like an arrowhead and then you've got a wiggly tail. So this is my photon.
Arrowhead with a wiggly tail.
Yeah, and depending on which way that tail wiggles, does it wiggle up, down, or left, right? Depends on the polarization.
All right, so if that works for you, listeners, then go with the arrowhead with the wiggly tail. Or you can think of a wave going up and down, or a piece of string wiggling up and down, left to right, that sort of thing. Anyway, that's what we're talking about when we're talking about direction of wiggle. So polarization is what?
So you have two types of polarization. You can wiggle basically one way, or you can wiggle the other way. And so they're looking for the signature of polarization in the cosmic microwave background, because finding that, we can find it the light wiggling one way, which is known as an E mode. And those E modes, we sort of know why they should be there. They should be there because the plasma that they basically formed in made them that way. So that's fine. We get that.
Fine. Okay.
Yeah, those photons are, we're cool with them.
That wiggle's accounted for. Good.
But we should see some of the photos wiggling the other way, which are basically B modes.
Okay.
And B modes should happen. Well, what couple of things can happen to them, but the one we're looking for that's happened to them is that inflation actually wiggled them.
Right. There's this period in the very early universe where the universe just blew up extraordinarily, should have changed the wiggle of the photons.
Yeah, and if you move matter around, we get this phenomenon which we feel quite familiar with now, called gravitational waves.
Right. We talked about that.
So in inflation, you had a lot of matter moving around.
Very quickly.
Very quickly. So you had a lot of gravitational waves produced, and we think that they should have changed these photons so that they have these B modes.
Okay. And no, haven't seen it?
We can't find them. We thought we had, But then it turns out that we just didn't take into account some other effects that were in the cosmic microwave.
Was this the thing that was reported on a while ago where there were observations from, I think it was from Antarctica?
Yeah,
where there
South
were,
Pole Telescope.
Yeah, and there was these huge announcements. It was almost on the scale of the announcements from LIGO and things like that, of the gravitational waves themselves, which was, hey, we've seen the polarization of these photons in the cosmic microwave background, and we've seen evidence for this stuff. And that then went very quiet.
Well, unfortunately, they had seen it. I mean, what they saw was real in the data.
Yeah. This is going back, about 5 years or something?
Yeah, 2014. So this BICEP
Yeah.
was the team that did this. And they did a fantastic job, and they pulled out these B modes. But we hadn't quite accounted for the amount of dust that was in that direction. And cosmic dust polarizes light all by itself as well.
Damn it.
Yeah, so Planck actually helped us clear that up.
Right.
But yeah, it was a bit annoying.
Yeah, because that was a big announcement. That was really big stuff. That was the first kind of round of, we've seen this, therefore gravitational waves. Like LIGO was, we're seeing gravitational waves themselves, the actual things. But the BICEP discovery was, we've seen evidence for these gravitational waves in the inflationary period of the universe. Like, that's what that is. Turns out, no, it's actually dust.
And it would have been the first detection of gravitational waves too. But
which is why that was so huge, except it wasn't. Which is a shame, but hey, that's science.
Yeah,
that's how it works.
We sometimes get it wrong.
Yeah. And you get it wrong because, there was this thing. We're not stupid. We just learnt now that there's dust. Okay, and that's what it does.
Yeah. So unfortunately, we haven't found it. And there's starting to be a little bit of a question. Probably
should have seen it by
now.
Should have seen it by now.
So there's some interesting stuff there.
These measurements are getting incredibly detailed, aren't they? Like if you go back to the original measurement of the cosmic microwave background with Besides and Wilson and their big horn, then that was basically just, the universe is at 2.7 degrees Kelvin. And then you start getting more detailed maps of the universe, and you can see some structure in it. But the earliest ones, was COBE the first?
COBE was the first satellite, space telescope.
Satellite measuring it. And the COBE maps were incredibly detailed, but really quite sort of broad brush. There's a bit of red over here and a bit of blue over there.
Low resolution.
Yeah, that's the word I'm looking for. And then it's been getting higher and higher resolution as you go along, to the point where now they're incredibly intricate maps of the universe. And we still not seeing these B modes.
Not yet.
And we should have.
No.
Now.
Well, that's the question. We probably should have. So it's interesting. And it's interesting to think about how that's impacted cosmic microwave background science now. Because Planck's finished. It's been set into a little safe orbit. It's turned off. It's fine. But
done the job.
Never going to talk to him again.
Nope.
So what's next, you're going to ask?
That's exactly what I'm going to ask. Where do we go from here?
Well, we don't have any big planned missions. Ooh. So that's the interesting thing. Have we done everything, all the science we can with the CMB? Probably not. Have we done the biggest, most
thorough, most complete study?
Well, I mean, sort of, have we got the easy stuff out? Probably.
Right. Yeah.
The biggest,
the low-hanging
headlines.
fruit.
Have we written most of the nature papers that we can out of the CMB? Well, maybe. But it's interesting. And I read an article actually whereby a lot of scientists who are working on the CMB are now moving into other areas because there's no data coming through. There's no new data now.
That's a worry. And yet there's still unanswered questions.
There's still unanswered questions, yeah. So it'll be interesting to see what happens. Yeah, so there are teams that are still going to work. South Pole Telescope and the BICEP team. I think they've got BICEP 2 now, a new upgrade to the telescope.
Especially now that they know about the dust.
Yeah, and they're doing lots of other science, of course, at the same time. We've really only skimmed the very, very surface of the cosmic microwave background. But, it costs a lot of money to put up a space telescope.
Yeah.
It costs a lot of money to put James Webb up.
Yeah.
So
and that's
I guess
still happening.
We can't do everything, can we?
So what started off as a joke by me, tongue-in-cheek, has turned out to be a really, really interesting episode about actual telescopes on actual balloons taking pictures of the sky that tell us not just about where the universe came from, but where it is now and where it's going next. And So I don't know if I could have been more wrong about that.
You'd have to try.
I could have tried harder, but I think actually I've scored peak wrongness on that particular joke. So I would like to formally apologise to everyone involved in any of the telescopes on balloons experiments around the world for the last, 30, 40 years. Sorry, everyone. Emily, listen, if people want to get in touch with us and just say, hey, Chris, that whole balloon joke thing, take that one back, or anything else, you've got questions, you've got comments, you just want to say hi, how can people get in touch with us here on the show?
Well, you can grab us on Twitter.
You can.
We are in the Twitterverse. So if you want to look us up, we are at SyzygyPod. That's SYZYGYPOD.
Well done. Well done. And it's not just Twitter, is it?
Oh, no.
We don't stop there.
It's all of the social media.
Yeah.
Every single one.
Yeah, go and find us. And we're probably at SyzygyPod out there somewhere.
Actually, I don't think we have Bebo. Does Bebo still exist?
Bebo?
No.
What's
okay.
Bebo? Is this a social
this is
media
what we
that I'm
had
not aware of?
had in my
Is this some kind of weird Kiwi social media? Is that what that is?
Possibly. It was when I
Bebo?
was a teenager. Bebo was all the thing, and you had your own sort of page, and it had horrible GIFs on it. And
Is this like some
do you
kind
remember
of...
MIDI files?
Oh, yeah. Yeah. Is it...
Yeah,
But is this
MIDI
some
files.
weird sort of Christchurch version of MySpace? Is that what that is?
It was kind of a cheap version of
Right.
MySpace.
Well,
yeah.
we're not on that. That doesn't exist anymore. But we are on most, if not all, of the others. We also have a webpage, syzygy.fm, and you can go there, find all our past episodes, all the show notes, the works. Go and listen to stuff that you haven't listened to before.
Do look at the beautiful plank results, because we'll put up some
Yep.
images of those, and because they're just stunning.
Oh, yeah. I mean,
we should be making wallpaper out of this stuff.
We should, actually. That's not a bad idea. Okay, add that to the to-do list for when I have time. But the other thing you can do on our webpage, of course, is go to the contact page and send us a little note and say hi. If you're looking for things to do, other than just contacting us, of course, the other thing you can do is give us a rating, give us a hello, give us a review on Apple Podcasts, Spotify, wherever you get your podcasts, your podcast source of choice. And the reason it'd be a good thing to do that is because it helps us to rise up through the noise and more people can find us. It really does help. So if you're feeling generous, you're listening to this and you're thinking, how can I give back? That's how. Go and give us a review. That would be absolutely lovely. But otherwise, that's pretty much it. Listen, over the next couple of weeks and months, I'm going to be on the other side of the planet, it turns out. I'm off to Australia.
the
It's my
cold
turn.
side for once.
Yeah, I mean, cold in inverted commas because it doesn't really get that cold. I'm going to be trading Yorkshire summer for Sydney winter, and it's pretty much exactly the same, just the days are shorter.
I don't believe you.
No, it's true. It's true. I'll send you the weather forecasts. Trust me, it's true. I'll be walking around in a t-shirt in winter.
With very, very soggy shoes.
Well, yeah, okay. It'll be raining, but then, this is Yorkshire. Anyway, point is, I'm going to be away, and so we might have a little bit of a slowdown on Syzygy. It might turn into sort of intentionally every 2 weeks rather than just randomly every 2 weeks. But we will continue going, and then when I'm back sort of towards the end of the Northern Hemisphere summer, we'll kick back into more of a regular gear again. But for now, I've got to go and pack a bag and get on a plane. What are you doing, Emily?
Marking exams.
Marking exams. Everyone send Emily lots of positive marking thoughts, and we'll catch up with you in roughly a week or 2 weeks' time. Catch you next time.
See you later.
Bye.